in the lab here. So good. So now that I actually hit record, we can start. Great. All right, so let me share my screen here. Katie, you're missing like half your shirt. I just want to tell you that. All right, so good. So capacitors. So capacitors are they're typical components which are found in electric.
A different color.
What's that?
I said it's just a different color. It's actually.
Oh, gotcha.
The sleeve.
I thought it was one sleeve on and one sleeve off, but that's okay. I'm not high fashion. I don't understand these things, but it's fine. So good. So capacitors are typical components which are found in electrical devices, which is what we saw in lab. So basically, the main purpose of capacitors are, number one, to store energy. So the ultimate purpose of putting a capacitor into a circuit is to store energy for some later use. And we'll talk about how they actually store energy and how much energy they can actually store. Other purposes are, as I mentioned in lab, these things are used in surge protectors. So again, they block flow of currents. So basically, if my house again got struck by lightning and I had a big surge going through my house, in that case, the surge protector, i.e. the capacitor in this case, would block that increase of energy and that increase of charge, which would keep my electrical devices from exploding, which would be great. They also act as ones and zeros in binary codes, such as RAM. So basically the way that works is it counts as 1 when it's fully charged and a 0 when it has no charge on it, or when it's storing energy. So it has maximum stored energy, it's going to be a 1, and when it has 0 stored energy, it's going to be a 0. So the way that it aligns itself would then create a binary code, which then acts as the memory or the RAM in your computers. So these are capacitors. So what actually is a capacitor? So basically what a capacitor is it is two conductors. So basically I have one conductor here. So this is a conductor. This one is also a conductor. And basically what happens is I'm going to take these two conductors, separate them by a distance. Let's call that distance D. And then these have some sort of geometry to them, but I'm going to separate them some distance, and then we're going to hook it up to a battery. So this is my battery, also known as an EMF. But we'll talk about that later enough. This stands for electromotive force. Motive force. So basically what happens is initially I'm going to take these two conductors which have initially 0 charge. So initially the charge on each one of these is 0. So they start off uncharged. So when I hook up the battery then is going to cause the charge carrier to move, which we're going to pretend is a positive charge. So it's going to move from the positive plate then onto this uncharged conductor, and it does that free of charge. So basically I can easily put that on there with no work necessary. So the amount of work it takes for me to put that first charge is simply equal to 0. But now I'm going to take a second charge. So let's say here's my second charge that I'm going to push through, which also has a positive charge. Meanwhile, I have over here positive charges also moving out back into the battery. So that on this side, I have a negative charge, right? So as this first one moves on, that then forces, by Coulomb repulsion, a positive charge to move out of here, which then leaves this guy negatively charged. So then the second charge, then I'm going to try to move from the battery then onto the capacitor, now has to overcome this Coulombic repulsion. So now I'm going to take this charge and try to push it onto the plate, but the plate now has a positive charge. So now as the charge gets closer and I'm trying to move it on here, there is a Coulombic force due to that repulsion trying to push this guy away. So for me to move this charge onto the plate, I have to overcome this Coulombic repulsion to put this second charge now onto the plate, which means it's going to take work. So now the work to put the first charge on here was 0, but to put the second charge is non-zero because now I have to overcome that Coulombic repulsion. So now I have this guy in here. Again, Coulombic repulsion causes on the opposite side to repel that positive charge in here. So the positive charge is going to move away, which leaves this guy now with a second negative charge. And this process keeps going. So now I'm going to move a third charge. The third charge I'm going to try to put on here, but now the Coulombic repulsion is even bigger because now there's twice the amount of charge on here. So now I have to do twice the amount of work to move it on, which means that every time I try to put a single charge onto this plate, the amount of work it takes for this to do it increases rapidly. Until eventually what will happen is that the amount of work it's going to take for me to put a single charge onto this plate, once it gets a full amount of charge on here, will become basically infinite. So I'll have to do an infinite amount of work, but my battery can't do an infinite amount of work, so this thing is going to reach some sort of maximum charge. So basically what will happen is that Q here is going to become the maximum charge at which this plate can hold. And this is going to become negative Q, which is then the negative maximum amount of charge that this thing can hold. So the maximum amount of charge then is going to be dictated by the battery itself. So as I have bigger and bigger and bigger batteries, I can increase the amount of maximum charge I can actually put on this thing because I can do more and more and more amount of work. So basically what that tells me then is that there is a relationship between the charge and the battery. So if I increase the size of the battery, I then increase the amount of charge, and it happens in a linear fashion. So if I plotted the potential versus the charge, or the charge versus the potential, what we find is that there's actually a linear relationship between these two quantities. So what this tells me then is that the charge is directly proportional then to the potential that I'm supplying across the plates. That constant is just equal to the slope of the line, which is what's known as the capacitance. So C here is what's known as the capacitance of the capacitor. Someone wants to join us. Right? So the slope of the line between the two of these is what's known as the capacitance, which is the capacitance of the capacitor. All right. So it turns out that for complicated geometries, the capacitance is actually very, very difficult to come up with, but it turns out that capacitance here is solely determined by geometry. So capacitance is solely dictated by the geometry of the capacitor, which basically means that as we change the geometry of that capacitor, we then change the capacitance of the capacitor. Now again, for complicated, I know how to spell, there we go, complicated geometries, the capacitance is very difficult to determine. So capacitance is difficult to determine. So here, if we want to know the capacitance of our capacitor in a complicated geometry, what we would have to do is actually just experimentally measure it. Experimentally measure. So, but if it has a simple geometry, then we can measure it. Or we can actually determine it. So we can, let's say, analytically determine it. So we're going to see how to do that for a simple geometry. But again, this is what's called a capacitor. So again, the capacitor, the point of having a capacitor is to store this energy. And the way that it stores the energy is by the amount of work it takes to put these charges on. So what happens then again is as I'm trying to move charges onto here, I get Coulombic repulsions that I have to overcome, which means the battery has to do work to overcome putting these charges onto the plates. And eventually what will happen is the battery just can't do any more work. So what happens then is the amount of work it takes for me to put these charges on gets stored as energy. So the energy which is stored here, the potential energy, is then equal to the work, which is then the work done by the battery to put charges on the capacitor. The capacitor. So this is a capacitor. Okay. Easiest way to measure capacitance is basically just to do an experiment. So again, here we would just put on a battery, we would measure the potential of the battery, we would measure the charge on the plates, and then from there we can determine the capacitance by using this expression. So I'm just saying that the capacitance then is equal to the charge divided by the potential. But again, in a simple geometry, we can actually determine exactly what the capacitance is of our capacitor. So let's do an example. Where am I looking? This one. So we want to know, for a simple geometry, here we're going to look at what's known as a parallel plate capacitor. So this is two sheets of charge, where one is positively charged, the other one is negatively charged, separated by a distance of d. And we want to know what is the capacitance of our parallel plate capacitor. So this is looking at from a side view. So here I have positive charges on this plate, negative charges on this plate, which creates an electric field. That electric field then points upward. So here then we have the distance d separating the two. We want to know what is the capacitance. So good. So let's look at that example. So let's draw. So here's my parallel plate capacitor. So here's my negatively charged one. So this has negative Q. Here is then my positive plates. So this has positive charges, positive Q. And what we know is that the charge, now this is only the charge on the positive plate. So when I write this down, this is the charge on the positive plate, is equal to the capacitance times the change in potential. So here, I'm going to have a potential across my plates. And these guys, again, are separated by a distance of d. So the capacitance then is equal to the charge divided by the potential across the plates. So we already know the charge that's given to us. The only thing we have to do now is determine, well, what is the potential across the plates? So what do we know? Well, we know the electric field inside the plates is given by a constant, which that constant then is equal to sigma, which is the charge density divided by epsilon naught. But we also know the charge density then is equal to the charge divided by the area, where the area then is the area of the plates. So if I was looking at kind of a topish view or an angled view of the plates, the area here would be the area of a single plate. So this is the area of the plate. On the plate. Now, since the electric field is equal to a constant, what that means is we can do all that stuff we talked about with potential yesterday, where we said that what the potential divided by the change in distance is equal to the magnitude of the electric field. So here, if I'm starting at point A here and I'm going to point B, then my change in distance here is simply equal to the distance between the two plates, or the gap separation between the plates. So this tells me then that the electric field then is equal to the change in potential divided by the distance between the two plates. So solving this tells me then that my change of potential across the plates then is equal to the electric field times the distance. But we also know the electric field is equal to the charge density divided by epsilon naught times the distance. Well, we know the charge density is the same thing as the charge divided by the area times the distance. So this is then my potential across the two plates. That's okay? Let's plug that in here then. So what this tells me then is that the capacitance then is equal to the charge divided by the potential, but the potential is the same thing as the charge divided by epsilon naught times the area times the distance. These two charges are the same, so they're going to cancel out. This is a 1 over a 1 over, so that moves to the top. So this is the same thing then as epsilon naught times the area divided by the distance. So this is the capacitance for a parallel plate capacitor. We're going to use this a lot. Okay. So what does this say? So ultimately what this tells me then is exactly the fact that the capacitance only depends on the geometry. So here we can see that the capacitance then depends on epsilon naught, which is a constant, times the area of the plates divided by the distance between the two. So everything here only depends on geometry. So only depends on the geometry of the plates. Now this is what you were playing with in lab, right? So in lab, you had that parallel plate capacitor, and what you were doing is you were changing the distance between the two. You were also changing the cross-sectional area of the plates, and what you were measuring then was how the capacitance was changing. So in this case, the capacitance then is changing. What this says is that the capacitance will go up if I increase the size of the area here, and it will go down if I increase the distance between the two plates. But if I decrease the distance between the two plates, the capacitance will also go up. And then what this expression tells me is that what? If I have a fixed battery, if the capacitance goes up, then the charge has to go down, or go up, sorry. And if the capacitance goes down, then the charge also has to go down. These two things are related to each other. So these are all the things that you saw in lab. It's mostly getting you ready for this part. Good, so now that we've seen this, let's do another example. This one. So this says, calculate the capacitance of a parallel plate capacitor whose plates are 20 centimeters by 3 centimeters and separated by 1 millimeter. Wants to know what is the charge on each plate if a 12-volt battery is connected across the two plates, and then what is the electric field between the plates, and then estimate the area needed to achieve a capacitance of 1 farad given the same gap distance. Okay. So let's do that. Great. So first things first, we know that capacitance for a parallel plate capacitor is epsilon naught times the area divided by the distance. Good. So what we're told here is, here's my parallel plate capacitor. What I know is that this is what? 3 centimeters. This is 20 centimeters. Is 3 centimeters, right? I have too many windows open. 7. Where's number 7? There it is. Okay. So yeah, 3 centimeters, and then it's separated by 1 millimeter. Good. Okay. So, and then there's the second plate down here. Here's my second plate. Good. And I know this separation distance here is 1 millimeter. Okay. 1 millimeter. Yeah. So first things first is it wants to know what is that capacitance. Good. So here we know the area then is going to be what? This distance times this distance. So first of all, we know the area is equal to 20 centimeters times 3 centimeters, which we're going to have to put into meters. So that's going to be 0.2 meters times 0.03 centimeters. That's my area, right? The distance here, d, is equal to 1 millimeter, which is equal to 0.001 millimeters. So for part A, we now know the capacitance then is equal to epsilon naught, which is 8.85 times 10 to the minus 12 as units then of what? Coulomb squared per Newton meter squared times the area, which is then 0.2 times 0.03 meters squared. So it's going to cancel a meter squared. All divided by then the distance, which is 0.001 meters. Plug in our numbers. We find in this case then that this has a capacitance of 53 times 10 to the minus 12 farads, which is the same thing as 53 picofarads. Okay, so pico is minus 12. It was okay? Not too bad, right? Part B then says, okay, let's take this capacitor and let's now attach this to a battery. So here's my battery, where my battery has a change of potential, which is equal to 12 volts. So now we want to know is that will cause a charge Q to store on this side, a charge negative Q to store on this side. So what is the charge which is being stored? Well, we know Q then is equal to the capacitance times the change of potential. So in this case, this is going to be what, 53 times 10 to the minus 12 times the potential, which is 12, which works out to be 6.4 times 10 to the minus 10 coulombs. Which is the same thing as 0.64 nanocoulombs. That was okay? Not too bad. Part C then says, what is the electric field? Well, again, we know the potential is the same thing now as the electric field times the distance between the plates, which means that the potential divided by the distance between the plates is then equal to the electric field. So this tells me then my electric field then is going to be equal to 12 volts divided by my distance, which is 0.001 meters. So this now tells me that the electric field is then equal to 1.2 times 10 to the 4th volt per meter. So one thing to point out with electric field is now there are two equivalent sets of units we can use for electric fields. So for electric field, we were originally saying that the electric field had units of newtons per coulomb. But now, because of voltage, we also know that this also has units of volts per meter. These two things are the same. Okay. There is no conversion factor between the two of these. Okay. So basically, if I wrote this as 1.2 times 10 to the 4th volts per meter, that is also 1.2 times 10 to the 4th newtons per coulomb. These two things are the same. There is no conversion factor between the two. It's okay? So finally, part D then says, okay, so let's say that now what we want is our capacitance to be equal to 1 farad, and we want the distance between the plates still equal to 1 millimeter, which is still equal to 0.001 meters. And we want to know now is what is the area needed of the plates to make this capacitor? This is what I want to know. Okay. Well, again, since it's parallel plate capacitors, we know the capacitance is equal to epsilon naught times the area divided by the distance, which means that my area then is going to be equal to the capacitance times the distance between the plates divided by epsilon naught. So the capacitance in this case is simply 1 farad times the distance, which is 0.001 meters, divided by epsilon naught, which is then 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Plug in my values. What I find in this case then is the area required is about 10 to the 8th meter squared. So this says that if I wanted to create a capacitor with 1 farad worth of capacitance using a simple parallel plate capacitor, the amount of area I would need per each plate is about 10 to the 8th meters squared. That is ridiculously huge. That is about the size of Boston, for example. So if I wanted to make a computer which needed 1 farad worth of capacitance, I would need a parallel plate capacitor the size of Boston to create that 1 farad capacitor. So typically what we end up doing is, in reality what we do is we use what's called a dielectric. We'll talk about dielectrics in a little bit. But what we usually do is you basically take kind of like aluminum foil, that's kind of your capacitor. You put paper in between, that becomes your dielectric, and then what you do is you roll it up. and then you roll it so that it becomes more of a cylinder. So that way you actually create capacitors, which are now smaller, so they're not just big capacitors like this way. But yeah, but that's just a ridiculous size that we would need. So,
Isn't that similar to the inner structure of a battery?
What's that?
I said, isn't that kind of similar to the inner structure of a battery? There's
Well,
like paper foil.
Depends on the battery that you're thinking of. An old traditional battery actually has acid on the inside, and we'll talk about the way that the battery works.
I think maybe I'm thinking of a lithium battery then.
Probably, yeah. So the lithium battery, what that does is, yeah, there's kind of like a paper between the two, and what that's supposed to do is, so that's more of a chemical battery, where you have chemical on one side and chemical on another side, and then what you allow is for them to permeate their way through a membrane, which is basically like a paper or something like that. So that way when they mix by permeating from one side to the other side, that's what creates the potential difference. And then when you charge it, what you're doing is you're actually causing those that permeated from one side to the other side to go back to their original separation. So it's kind of like starting off with men on one side, women on the other side, and then they mingle. And then you say, okay, now you got to go back to your lines, right? Separate everybody again. So that's basically the way that a chemical battery works. But an old structure type battery, and we'll talk about one of those, is actually has an acid on the inside and two pieces of metal. And what the acid actually does is it corrodes the one, causing it to strip off electrons, and then the other one pulls off positive charges to basically cancel that off, which basically leaves one positively charged, one negatively charged, which creates the potential difference. So. But yeah, newer batteries, they have that membrane on the inside, which causes for slower permeate, for them to pass through the membrane. That's right. All right. So good. So these are capacitors. Like I said, any other type of capacitance, which is more complicated than a parallel plate capacitor, the easiest way to measure it would be to just simply experimentally verify it. So by, again, measuring the potential, measuring the charge, and then determining the capacitance that way. So the only one that we're going to be interested in is this parallel plate capacitor. So next thing we want to talk about is the energy which is stored. So how much energy is stored? So again, the reason that this thing saves energy is because, again, we have to do work. So again, if here is my capacitor, again, what's happening is the battery has to do work to force charges. So this is my Q onto this, which already has charge onto it. So by me having to do work, what happens then is that my capacitor will actually store energy, and it stores it in the form of potential energy, where that potential energy then is simply equal to the work which is being done. I'm not going to bother deriving this for you. I'm just going to write it down. So hopefully everybody forgives me. So it turns out that the energy which is being stored, so the amount of work that I have to do to cause this to happen, is then equal to 1/2 the charge on the capacitor times then the change of potential across the capacitor. So again, if this has a delta V across the capacitor, which is equal to that of the battery, has a maximum amount of storage of Q, then the amount of potential energy which is stored, which is equal to the work which is being done by the battery. So this is then again by the battery. Again, is equal to 1/2 then the charge, where this is the maximum amount of charge. And then this is going to be the potential across the plates. Now, I'm going to specifically say potential across the plates and not specifically the potential from the battery, because as we also saw in lab, is if I have capacitors put up in parallel in series, they don't always have the same potential as the battery. So this is going to be the potential across the plates, not necessarily potential from the battery. Now, if we also use that Q is equal to C times delta V, we can actually rewrite this in several different forms. So if I use that, I can rewrite this then as 1/2 times C times delta V times delta V. So here I'm just replacing Q with C delta V. So this is also equal to 1/2 C times delta V squared. Or I can write delta V is equal to Q divided by C. So I can also write this then as, let's go back to our first one. So I can also rewrite 1/2 Q delta V as then being 1/2 Q times Q divided by C, which is then 1/2 Q squared divided by C. So basically, what we can have then is the work done, which is equal to the potential energy, is then equal to one of three forms. So it's either 1/2 the charge times the potential across the plates, or it is 1/2 the capacitance times the potential across the plates squared, or it's 1/2 times the charge stored on the plate squared divided by the capacitance. Any one of these three are the same thing. So all of these represent the energy which is stored. What's the difference? The difference is mostly how you want to think about the energy being stored. So either you can think about the energy being stored in the charge. So again, what's happening is I'm trying to push these charges onto the plate, so the energy is stored in the fact that I'm pushing these charges onto the plate. So basically, that's kind of what these two are saying. These two are basically saying that the energy is stored in the charge. This one is saying, well, the energy is actually stored in the potential. So this is saying that the energy is stored in the potential across the plates. Or a third way to look at it is we can think about the energy actually being stored within the electric field itself. Because what's also happening is that, remember, there is an electric field inside the plates, where that electric field is pointing down in this direction. So we can actually also rewrite this in terms of the energy being stored within inside of the electric field. So let's talk about that one. So here, again, what we know is that the potential is equal to the electric field times the distance. Let's say this is a parallel plate capacitor, so this is equal to epsilon naught times the area divided by the distance. So this says then that the potential energy is equal to 1/2, again, the capacitance times the change of potential squared, which is then equal to 1/2 epsilon naught times the area divided by the distance, times then the electric field squared times the distance squared. This distance cancels out this one, so this is now going to be equal to 1/2 epsilon naught times the electric field squared times then the area times the distance, but area times distance is the same thing as the volume. So this is then equal to 1/2 epsilon naught times the electric field squared times the volume. And this one is volume. So this is the volume contained within inside of the plates. So what this one says is that the potential energy is actually stored within inside of the electric field. This is within the electric field itself. Now, typically with this one, we define something else. That something else is what's known as the energy density. So let's define the energy density. So energy density is equal to little u, where little u then is the potential energy per unit volume. So this is the potential energy per volume. Okay. Anyways, so if I take this quantity here and I divide that by the volume, the only thing that's going to happen is this volume piece is going to go away. Right? So this is then equal to 1/2 epsilon naught times the electric field squared. So this is the energy density. So the energy density says that the energy stored, or at least the energy per unit volume, which is stored between the plates. So again, if here are my plates, is stored in the electric field itself, which is pointing from the positive plate to the negative plate. So what the energy density then says is if I take a small volume here, so here's my volume that I'm looking at, so this is my volume V, then the energy density is telling me how much potential energy is stored within inside of this area. Okay? So this is what U is. So U is just telling me that if I take U and multiply by that volume, then that's equal to the potential energy. So it just means inside of this little tiny volume, this is how much energy I have stored within inside of this volume. Okay, that's what U is. U with delta V. There we go. Okay. So this is what's called energy density, so little u. So again, the energy which is stored then by the capacitor comes from the fact that we have to charge it by doing work from the battery. As the battery does more and more and more amount of work, that means more and more energy is available for us to use at a later point in time. So the energy is stored from doing work onto the battery, or sorry, onto the charge via the battery. And again, we can write this one of three ways. We can either write it the top one, middle one, or bottom one. Which one you usually use just depends on what it is that you know. So if you know the charge and you know the potential, you'd use the first one. If you know the capacitance and the potential, you'd use the second one. If you know the charge and the capacitance, you would use the third one. And each one just depends on which one it is that you know and how you want to think about the charge or the energy being stored. Is it being charged within the potential? Is the charge being stored within inside of the charge? Or finally, is it being stored within inside of the electric field itself? So good. So this is then energy stored. So I'm going to talk about one more thing, and then we'll do an example using this. Okay. So last thing I'm going to talk about is that thing I mentioned earlier, which is what's known as a dielectric. Let's talk about dielectrics. So what's a dielectric? So a dielectric is a way to increase the capacitance of a capacitor. So it's a material which is placed inside of a dielectric, or sorry, the dielectric is placed inside of the capacitor to then increase the capacitance. So here is, say, one plate of my capacitor. Here is, say, the second plate of the capacitor. Then the dielectric is usually some sort of material that we're going to jam in between the two, which then is going to increase the overall amount of capacitance. So what is a dielectric? A dielectric is an insulator. So this is an insulator, or an insulating material, which increases the voltage we can put onto the capacitor. Okay. The way that this works is the following. So everything has a natural point at which the potential gets so high that it has to discharge. This is what's known as the breakdown potential. So basically what will happen is air, for example, what happens is once the potential becomes so great, you ionize the air. So what happens is that it has to discharge in the way that it actually strips off electrons from the air itself, which then causes typically a spark. So what will happen is if you have a whole bunch of charge on you and you start reaching out for a door handle, especially in the wintertime, what will happen is you will discharge because the potential between your fingers and the door handle becomes so great that you'll actually create lightning between your finger and the door handle. And this mostly happens because of the air itself. The air has reached a point where it will ionize the air by stripping off the electrons. Okay? An insulator, what that basically does is all insulators have a breakdown potential which is actually higher than that of air. Okay? So what happens then is that this dielectric is classified by what's known as the dielectric constant, which is determined by its percentage away from the breakdown potential of air. So the dielectric constant, we're going to call that capital K, one more K, yay for Ks, is equal to the dielectric constant, which is then related to the breakdown potential of the insulator divided by the breakdown potential of air. So this is what's called the dielectric constant. So the dielectric constant is a number which is dictated by the type of insulator that I have. So different insulators will have different types of dielectric constants. So for example, plastic has its own dielectric constant, wood has its own dielectric constant, and etc. So again, this is some sort of insulator which is placed inside of the capacitor to then increase the capacitance, which allows for also a greater potential which is allowed to be put onto the capacitors. Since the potential becomes bigger, that means we can also put more charge onto it as well. Okay. Now, why does this work? Well, what happens is, let's think about our insulators. So we talked about insulators before, and the fact that if I put some charge near it, what will happen then is I polarize the dielectric. So what will happen is the insulator gets a small polarization on the inside, so I'll get positive charges separated then from negative charges, but only by a small amount. Right? So I have positive charges, negative charges, which then creates these little dipoles. So I'm going to polarize my material. So inside of here, I'm going to create these little tiny dipoles. But since I have charge separation basically between the two, what will happen then is I create also an electric field inside of each one of these, which then is going to, in this case, point in this direction. So this is the electric field created by each one of these different little polarizers, which means that I'm going to create a much larger electric field. So what's going to happen is I have an electric field, which say points downward, in this case, from the positive charges on here, right? So this is going to become then the electric field. But I'm also going to induce an electric field on the inside. So this is the electric field from the plates, but I'm also going to induce an electric field basically on the inside, which then will increase or decrease the overall size of the electric field depending on how these things are going to line up. Now here, what that'll do then is that'll also increase the amount of potential, which will then allow for me to put on more charge and more potential across the plates. Okay. So ultimately what happens then is that the point of putting in a dielectric is that it increases the capacitance from C to a new capacitance, let's call that C prime, which has been increased by the amount of the dielectric constant. So by putting in the dielectric, what that does is it increases the capacitance by an amount of the dielectric constant. So the point of this is to increase the capacitance by an amount of the dielectric constant. So this is the point of the dielectric. So again, the dielectric is simply an insulating material which we put inside that then is going to increase the amount of capacitance by increasing it by an amount of the dielectric constant. So what effect does that have onto my circuits? Okay, so let's say here is my capacitor. So I'm going to pull this guy out again. Let's play with the dielectric setting in this case. I'm going to put my potential on 1 volt, and we want to see what happens to all of our different quantities. Okay, so here I'm going to measure the potential difference across the plates. We're going to measure the capacitance, the charge, and the energy which is being stored. So notice that if I take my dielectric, this is my dielectric, and I start putting it inside of the plates, what will happen is that the capacitance goes up, the charge goes up, and the energy which is actually being stored all go up. But the potential itself stays fixed. So if I put in this dielectric constant or this dielectric material, while the battery is connected to the capacitor, the potential stays the same, which causes the capacitance to go up, the plates charge to go up, and the energy stored to go up. Okay. So in this case, let's write all that down. So if we insert while connected to a battery, what happens in this case then is we get a new capacitance, which is equal to the original capacitance times the dielectric constant. The charge, we get a new charge, which is equal to the original charge, also times the dielectric constant. And the energy stored also goes up by an amount of the dielectric constant. So when I insert the dielectric while it is connected to the battery, again, the capacitor goes up, the charge goes up, and the energy stored all go up by an amount of the dielectric constant, but the potential difference stays the same. Okay. Now, the reason that the potential difference stays the same is that the potential, again, is being fixed by the battery itself. So in this case, it can't change because it's being fixed by the battery. So this is the same because it's fixed by the battery. Now, to go back to here a little bit. So as you can see, as I'm moving this thing in, I'm getting polarization on the inside. So here, this polarization is causing the negative charges move to the top, positive charges move below, which means that actually the electric field, if I draw the electric field lines on here, will actually be opposite to the direction of the electric field itself. Which basically means that if I measure the electric field before and after, so initially if I put this guy in, initially the electric field is 150, but once I put the dielectric in, the electric field then is going to become, I'm sorry, between the plates actually increases, sorry. It comes to 750, which allows for more charge to actually be able to go on. Okay. So good, let me take this away. So now let's do the same thing. Let's disconnect the battery this time and see what happens in this case. So now, when I push this guy in, notice what happens is now the capacitance still goes up. The charge now stays the same, because now if I move it out and I push it in, the charge stays the same. But now the energy goes down instead of up, and the potential also goes down. So if I insert the dielectric while it's disconnected from the battery, the potential drops, the capacitance goes up, charge stays the same, but the energy stored decreases. So let's write all that down. So while it's disconnected from the battery, again, the new capacitance increases, so it still increases by the amount of the dielectric constant. The charge stays the same. We'll talk about why that happens in a second. The potential energy now decreases by an amount of the dielectric constant. And the potential also decreases by an amount of the dielectric constant. Okay. So this is what happens when we insert it while it is disconnected from the battery. Good. Now, the reason that the charge stays the same is, so let's look at what's happening. So as I'm moving this thing in, you can see the charge kind of shifting around and moving, but the reason the charge doesn't change is because the charge now has nowhere to go, right? Because once I use the battery here, so if I connect it back to the battery, so initially if I put this at 0 volts, there is no charge on the capacitors, but once I now start to increase it, I now put a maximum amount of charge on here, which means that the charge can only move because it's connected to a wire. So as soon as I disconnect the battery and there is no wire, the charge now can't go anywhere because it can't jump off of the metal. So as I start to move in the dielectric, the charge will move around and do different things, but it's forced to stay within inside of the plate. It can't jump off and spontaneously go to the other plate or go back into the battery or go anyplace else because there's no avenue, there's no wire for it to actually do that with. So this is actually bound to the charge plate itself. Okay? So the reason that the charge stays the same is because it can't go anyplace else. So the charge is bound to the plate and can't go anyplace else. Okay. So even though the capacitance is increasing, but the charge is staying the same, again, what happens in this case then is that the energy will actually go down, and it goes down by an amount of the dielectric constant because the potential also goes down by an amount of the dielectric constant. So these are dielectrics. So again, the point of a dielectric is to increase the overall capacitance of the capacitor. And again, the reason for that is that the reason we want to do that is because we want to be able to put more potential over the plates, because it's not going to break down as quickly as an air-gapped one, which allows us to be able to store more charge, which allows us to be able to store more energy. So this is the reason for putting into dielectric. So good. So let's use all of this, and let's do an example. So this one says, I have a parallel plate capacitor filled with a dielectric constant of 3.4. It's connected to a 100-volt battery. So then it says, after the capacitor is fully charged, the battery is then disconnected. Okay. So then it says the plates have an area of 4 meters squared and separated by a distance of 4 millimeters. So it wants us to find the capacitance, the charge, and the electric field strength, and the energy stored in the capacitor. Okay. So let's look at all that, and then we'll talk about part B. Okay, so what's happening is we have, here is our plates. Okay, I'm going to connect this guy to a battery, where the battery has a potential which is equal to 100 volts. So that across my plates then I have a 100 volt potential. So this is equal to delta V. That's going to cause this side to become positively charged. So I'm going to have a Q on here. This side is going to become negatively charged. So I get a minus Q. And what I know is that this is my distance D, which was 4 millimeters. And these guys have an area which was equal to what? 4 meters squared, if I remember correctly. Okay. Okay. So part A wants to know, what is the charge? Okay. Oh, and this is filled with a dielectric. Sorry about that. Where the dielectric has the dielectric constant, which was equal to 3.4. Okay. So dielectric constants, one thing I should mention, will always be greater than 1. It's equal to 1 when it's equal at air. So if this was air, so any other dielectric will have a dielectric constant greater than 1. So good. So it wants to know, what is the charge? Wants to know what's the capacitance. Wants to know what's the electric field. And what else did I want to know? The energy stored, is that right? Yeah, any energy stored. Okay, great. And what is the energy stored? So the potential energy. All right. So let's start off with the capacitance. So here we know the capacitance is then equal to the dielectric constant times the original capacitance without the dielectric constant. This is a parallel plate capacitor, which means this is going to be equal to the dielectric constant times epsilon naught times the area divided by the distance between the plates. So this is going to be equal to 3.4, which is the dielectric constant, times 8.85 times 10 to the minus 12 for the epsilon naught, times the area, which is then 4 meters squared, divided by the distance between the plates, which is 0.004. Look at our numbers. We find in this case then is, so I get to my question. This is about 3 times 10 to the minus 8 farads. It's okay. The charge then is then equal to, well, in this case, we know this is going to be equal to the capacitance times the change of potential, right? This is our charge. So it's going to be equal to 3 times 10 to the minus 8 farads times then a potential, which is then 100 volts. So our charge then is going to be equal to 3 times 10 to the minus 6 coulombs, which is 3 microcoulombs. It's okay. Our electric field, we now know is what? The change of potential divided by the distance between the plates. So this is going to be equal to 100 volts divided by 0.004 meters, which is then equal to what, 25 kilovolts per meter. So it's 25 times 10 to the third. So 25 times 10 to the third volts per meter. It's okay. Finally, the energy stored. Well, we know the energy stored, so let's look at what we know. So we know the capacitance, we also know the potential, so let's use that this is 1/2 the capacitance times the change of potential squared. So this is going to be equal to then 1/2 times the capacitance, so it's just 3 times 10 to the minus 8 times the potential, which is then 100 squared, which is then equal to 1.5 times 10 to the minus 4 joules. So that's my energy stored. Are we doing okay? Not too bad? Good. So the next part then says, for part B, so B then says the dielectric is now carefully removed so that the distance and charge stays the same. So find the new values of the capacitance, the electric field strength, and the voltage between the plates, and the energy stored in the capacitor. Okay. So basically what's happening now is what? We disconnect it from the battery so that this thing has what? The dielectric constant on the inside has the amount of charge, which we calculated as Q. Still the same separation D, but now what we're going to do is we're going to take this dielectric constant, or this dielectric object, out. So now we're going to pull this guy out while it's disconnected from the battery. Okay. And now what we want to know is, after we do that, what is the brand new capacitance? What is the brand new charge? What is the brand new electric field? What else do we want to know? What is the brand new energy which is being stored? Now, let's go back to what we talked about before. What we talked about was that this was when we inserted the dielectric while it was disconnected from the battery, which means that if we pull it out, the opposite of all of these things are going to be true. Which basically means that, again, if I took my insulator and I put it inside of my plates while the battery is disconnected, we said as the capacitance went up, the charge stayed the same, the potential went down, or sorry, the energy went down and the potential went down. But that's when I put it in. So if I pull it out, the inverse of this must be true, right? So if I pull it out, what would have to happen then is the capacitance would have to go down, the charge would stay the same, but the energy would increase and the potential would also increase. Right? So here, since we're doing the opposite of this, then the opposite has to be true. Okay, so here, since removing, not adding, the opposite must be true. So this means then that what? The new capacitance must be equal to that original capacitance, but now divided by the amount of the dielectric constant. So this was then 3 times 10 to the minus 8 divided by 3.4, which is then equal to 8.8 times 10 to the minus 9 farads. The charge must stay the same, so Q must be equal to Q prime. So in this case, this is just equal to, what do we have? 3 microcoulombs. The potential energy, or the energy which is being stored, must now increase by an amount of the dielectric constant. So now that's then going to be equal to 3.4 times the original energy, where that energy was what, 1.5 times 10 to the minus 4, which is then equal to 5.1 times 10 to the minus 4 joules. Now for the electric field, we first have to know what happens to the potential. So again, we know that the potential then is going to increase by an amount of the dielectric constant, which means this is going to be 3.4 times 100, which means the potential now goes up by 340. The electric field is equal to, again, the change of potential divided by the distance between the plates. But since I'm not changing the difference between the plates, then this is just going to be 340 volts divided by 0.004 meters, which gives me a new electric field of 85, let's see. Yeah, because it went up. 85 kilovolts, or 85 times 10 to the third volts per meter. Okay. So we're now done. 12 minutes to spare. 11 minutes. So that's all the material we need for the exam. So let's talk about the exam. Let's do a quick review for the exam, and then I have a whole bunch more group assignments for you. They're all up on Blackboard, but I'll show them to you so we can kind of talk about them real quick. So this exam is going to cover what, chapters 16 and 17. So let's talk about chapters 17 first, or sorry, 16 first. So chapter 16. So chapter 16 is, so basically first we're looking at force. So our general electric force is equal to the charge times the electric field. And when we have force between 2 point charges, this is the Coulomb's law, which says that the electric force then is equal to little k times Q1 times Q2 divided by R squared. That's the magnitude of that force. So this is our general expression, and this is between 2 point charges. If I have more than 1 point charge, then we say the force is then equal to the sum over all of these individual forces. So if this is the force on the first charge, then this is equal to the force on that first charge by all the other charges. Okay? This was the superposition. So again, here this is just saying if this is Q1, this is Q2, separated by a distance of R, then again, how this force is going to interact depends on if I have unlike or like charges. So if I have unlike charges, this will become an attractive force. So the forces will be towards each other. So it's force on 1 by 2 and 2 by 1. But if I have like charges, then this will become a repulsive force. So this is a force on 1 by 2 and force 2 by 1. Okay. From there, we talked about electric fields. So remember, electric field in general is equal to the force divided by the charge, which means that for a point charge, the electric field is equal to K times Q divided by R squared. So this is the magnitude of the electric field, and this is for a point charge. And again, this satisfies the superposition. So the total electric field at a given point P is equal to the sum of all the individual electric fields at that point. So this is our, again, superposition. Okay. And then the final thing we looked at was a dipole in this chapter. So we had the dipole moment, P was equal to the charge Q times then the distance written as a vector between the two charges. So here I have a charge negative Q, here I have a charge of positive Q. And then they're separated by this distance d. So d then points from the negative charge to the positive charge and has a magnitude which is equal to the length between the two charges. Here, we saw what happened if I put this guy into an external electric field. So here, if my electric field points this way, so that this is an angle of theta, we saw this manifests itself as a torque, where the magnitude of the torque is then equal to the dipole moment times the magnitude of the electric field times sine of the angle between the two. This also has a potential energy associated with it, which is then equal to minus the dipole moment times the electric field times cosine of the angle between the two. So this is the torque by the field. And then this is the energy in the field. So that's it. So that's all chapter 16. So not too bad, just a few things. Not too bad. Let's go to another page, talk about chapter 17. So chapter 17 is what we just finished up. So chapter 17, we now have potential. So in this case, we know that the change of potential energy is equal to the charge times the change in potential. The work is equal to negative change of potential energy, which is then equal to negative the charge times the change of potential, which is also equal to negative Q times E times D when E is equal to a constant. Then we have that the change of potential is equal to negative the electric field times the displacement times cosine of angle between the two, which tells me then that the magnitude of the electric field is equal to negative of the change in potential divided by the distance. Or let me write that as delta x. And again, here I'm assuming that these two things are parallel. So here I'm assuming that the electric field is parallel to delta x. We have the potential at a point P for a point charge. That's given by this guy. Divided by him. So this is for a point charge. And again, this is relative to spatial infinity. Relative to infinity. So if this is my point charge Q, this is my point R, or my point P at a distance R, that's the potential there relative to what it is at spatial infinity. And if I have more than one point charge, then the total potential at that point is then equal to the sum over all of the potentials at that point. Now we have capacitance. So we know that charge is equal to the capacitance times the change of potential. So this is for capacitors. We have capacitance is equal to epsilon naught divided times area divided by the distance. This is for parallel plate capacitors. We have the energy which is stored is either equal to 1/2 the charge times the potential, 1/2 the capacitance times the change of potential squared, or 1/2 the charge divided by the capacitance, or the charge squared divided by the capacitance. There we go. Energy density, don't worry too much about that for the exam. I'm not going to ask you about that on the exam. Other things to note is when, for dielectrics. So here we have a new capacitance, which is equal to the capacitance times the original capacitor. And then we have those where it's connected. So when it's connected, what happens in this case is the potential stays the same. the charge increases. And the potential energy stored also increases. When it is disconnected, the charge stays the same. The potential decreases. And the energy also decreases. Okay. That's okay? So let's talk about some possible problems. So our two long problems, the first one is going to concentrate more on this guy. Those will be our first long problem. Long problem number 1. So basically, this is going to be like those ones where the group exercise, which basically had a charged particle moving between parallel plates, feeling a force and being deflected and things like that. So that's going to be more of this guy. So this would be things like parallel plates. Again, a charged particle with initial velocity moving between the plates gets like deflected, for example. So it'll be similar to this. The rest of the stuff would basically be things like short answers as well as extra credit, so stuff like that. So the second long problem is basically going to deal with all the things we talked about today. So basically this type of stuff. So capacitors with dielectrics, so all this kind of stuff here. So this will be the second long problem. So long problem number 2. Okay. One thing I should mention is this will also find its way into long problem number 1. So basically a relationship between the electric field and the potential. So kind of like what we were doing today towards the end there. So okay. So let's talk a little bit about some other stuff here. So get rid of these. So even though we are officially out of time, I do have a bunch of group projects for you. So let's kind of quickly talk about those, and then you guys can work on them in your free time. Okay, so the first one is going to be this one. So this is a small metal sphere which carries a charge of Q1, is held stationary by an insulating support. A second metal sphere with a net charge of Q2 and a mass is projected towards Q1. So when the two spheres are about 0.8 meters apart, Q2 is moving towards Q1 at 22 meters per second. Ignore the effects of gravity. What is the speed of Q2 when the spheres are 0.4 meters apart? And then how close can Q2 get to Q1? So let me quickly draw kind of what's going on here. So just means somewhere over here, this has charge Q1. This thing is being held fixed in space. Q2 is over here, initially moving in this direction with initial velocity of v0, and this thing is separated by, what was it, 0.8 meters, I think? And it tells you the charge and the mass that this guy has. So this guy has a mass. So what part A is basically asking is, by the time this thing reaches this position, so that this distance here then is 0.4 meters, how fast is this thing going? Okay. So what's happening is it tells you this is a negative charge, this is also negative charge, which means that you should have a Coulomb repulsion, which means this thing has to be moving slower. Right? So by the time he gets 0.4 meters away, he has to now be moving slower. Just making sure I have my distances right here. Yeah. So finally, what it wants to know is how close can this guy get where he's going to momentarily stop. So part B is basically saying, use a different color, is how close is Q2 going to get to Q1 where the final velocity is going to be equal to 0. So let's call that V prime will be equal to 0. So it wants to know this distance here. So what is R? So it wants to know how far can this guy get when the final velocity, call that V prime, is equal to 0. So it has to momentarily stop. At that point, it would just turn around and fly all the way out to infinity. Okay. It's okay? Well, not too bad. This one is mostly just conservation of energy. So this one you're just saying that what? The change in kinetic energy plus the change of potential energy, which is going to be the charge times the change of potential, will be equal to 0, where the potential in this case will be that of a point charge. So this is going to be KQ over R, so of a point charge. Great. Now we have the second and third one. So the second one says we have 2 electrons are fixed 2 centimeters apart from each other. Another electron is shot from infinity and stops midway between the 2. What is the initial speed? So let's draw what's happening there. So this is the next one. So this one's saying I have an electron here, so these 2 are 2 centimeters apart. Now somewhere out here, I'm going to take a third electron at R is equal to infinity with some initial velocity V0. And I want is for this guy to come flying in and then stop right here at the midway point between the 2. So it's going to be the last location of that last electron. So in this case, we know that the final velocity then is going to be equal to 0. So from this, I want to know, again, what is the initial velocity? So this, again, is conservation of energy. So we're going to use the change in kinetic energy plus Q times the change in potential energy is equal to 0, where, again, now our final velocity is going to be equal to 0. And the potential, again, will be given by point charges, so KQ over R. But here I have 2 point charges instead of 1. Okay. The third one then says, in the figure below, point P, which is at the center of this rectangle. So it says, with the potential equal to 0 at infinity, what is the net electric potential at point P due to these 6 charges? So basically here we have to be a little bit careful, because before, if we were dealing with electric fields, we would say that the electric field from this charge and this charge would cancel at P, as well as this charge and this charge, because the electric fields would be equal and opposite to each other. But potentials, remember, don't have directions, which means that this potential from this guy and this guy don't cancel because they're not in opposite directions. And the potential from this guy and this guy won't cancel because they're also not in different directions. But the potential from him and him would cancel because this one is a negative charge, while this one is a positive charge. So this distance is the same, and then the charge here is being negative and negative. So basically, this potential will cancel from this potential, but the rest of these will just sum together. So that's that one. What else I got for you? Good. One more. Okay. So this one's a parallel plate capacitor one. So this one says we have parallel plate capacitors with a plate area of 8.5 centimeters squared and an air-filled separation of 3 millimeters are charged by a 6-volt battery. They are then disconnected from the battery and pulled apart without discharging to a new separation of 8 millimeters. So find the potential difference between the plates, the initial energy stored, the final energy stored, and the work it takes to separate the plates. All right? So basically, what does that mean? So it means initially, I'm going to take these plates. So here's plate 1, plate 2, connect these guys to now a battery, where that battery now has 6 volts worth of potential. And these guys are separated by initially 3 millimeters. So this is going to get a charge of Q. Now I'm going to disconnect it from the battery. So that now here's this plate with exactly the same amount of charge Q at still that 3 millimeters. But then what I'm going to do is I'm going to pull these guys apart. So I'm going to pull these so that afterward, these plates are going to now be separated by a much greater distance, where this new separation distance, called that d prime, was equal to what, 8 millimeters? Yeah, 8 millimeters. But this charge here has to stay the same. So basically what it wants to know is, ultimately, how much work did I do to pull this thing apart? And did I do the work, or did the electric field do the work? Now, as far as the exam is concerned, this is a great example of the second problem. So make sure you understand basically how to do this one. And I think there's an example like this on the practice as well, which reminds me, did I post the solutions for the practice? I don't remember. I'll take a look afterward, so that's fine. All right, so listen, so as far as the exam is concerned, this is a great example. So basically go through and make sure you know how to do this, because the one on the exam will be something similar to this. Okay. Except it'll also involve dielectrics. So, sorry to keep you over. Anybody have any questions on anything? It's kind of a quick barrage of a whole bunch of different stuff, but. Your shirt's still throwing me off, Katie. It still looks like skin. That's fine. I see. All right. So, was okay? All right, so hopefully I'll get your first exam graded over the weekend, so at least you know what you got on that one going into this one. Same thing, I'll set up everything on Blackboard, so that way all the extra credits and group assignments and all that stuff you can post before do the exam. Same thing, the exam will automatically show up at 8:55, and then we do at 10:45, same thing as last time. And if you have any questions or anything over the weekend, go ahead and email me, or if you need, we can try to set up some sort of Zoom stuff if I can find time. Okay. So, everyone's okay? Not too bad. Good. So, and then, yeah, so then Tuesday we'll start the next part, or then the next exam. That stuff is mostly just mindless algebra, so that'll be a lot easier for everybody to kind of understand, but it'll be great. Okay. So have a great weekend. Try not to stress too much. Life will be wonderful. And I will see everybody soon.